tropical homotopies two ways.
Yes, thank you very much for the invitation. Thanks for this. Yeah, so thanks for the invitation to this really wonderful conference. I went through the different abstracts that were uploaded on the website and make a list of names of people I have to talk to. And by the pigeonhole principle, there will be a coffee break where I have to talk to two people at the same time, at least one. So I'm here to talk a little bit about tropical homotopies, and namely two different types of tropical homotopies. Now, unfortunately, I'm not really good with coming up with names, so I just gave both of them the same name, tropical homotopies. If there are any suggestions on better names, these papers are not published yet. I can still change it. But let's do. So okay, I'll just start very briefly with some motivation. So I'm I guess more of the applied algebraic geometry crowd. So basically everything I'm going to say is just motivated by polynomial system solving. Okay, thanks. Okay, yeah, so is it? Okay, it works now, thanks. Yeah, so basically what I'm interested in is, okay, let's just move forward. So basically you have a polynomial system. This can come from whatever application. This can come from some kind of, okay, so this is a picture of the BMW factory in Leipzig, if you want to know. This can come from there, where you have to, a robot arm that has to reach a specific point. This can come from computing bitangents of a plane quartic surface, a curve or something like that. So basically, I'm interested in numerically solving this polynomial system as you see in front of you. And so one thing, yeah, one very prominent source of these things are these inverse kinematic things. So these are basically robots where basically people from engineering, they try to come up with a robot that performs a certain motion, and it basically boils down to polynomial equations. And they're really interested in getting all the solutions because they want to prove that their robot, that the robot that they designed is kind of optimal. And for that, they need to be able to compute all possible robots capable of doing a certain movement. And this boils down to just solving a polynomial system. And another application that I care deeply about, and that's the final one I'll talk about today, is these chemical reaction networks. So you should all know these from high school, if you had chemistry in high school. These are these reaction arrows. Now, if you're basically in industry, these reaction arrows also come with reaction rates. So certain reactions are more likely than others. And if you basically try to model the dynamics, if basically you have just one big pot of chemicals, again, polynomial systems. I will not say too much about this, but yeah. So for example, the first polynomial is the change of the concentration of element A. And for example, this 1.4 xa, xb, xc comes from the fact that there's an arrow with 1.4 going on the up, from left to the right. And it starts at A plus B plus C, which corresponds to this monomial. And this is just the reaction rate. And as you go from left to right, you can see you gain 1a. You have 1a on the left, 2a on the right, and this is why there's plus 1.4. This is how these things arise. It's quite nice. Okay, but enough of applications. Let's talk about how to solve these things. So if you have, let's say, more generally speaking, let's just in algebra, you have a polynomial ideal. For the sake of simplicity, I'll just assume that K is algebraically closed. So you have a zero-dimensional ideal, and you want to kind of solve it. Then there's one way to do this, and that's symbolically, and I'll just talk about it very briefly because this is not what we're going to do in the talk. But depending on where you grew up academically, this is the go-to way to solve it. Basically, what you can show and is that if you basically apply a generic choice of transformations, so basically this is like a map, and this new xn is a random linear combination of the old xn, well, now suddenly every zero has a unique coordinate in xn, if these lambda were chosen generically. Hence, your ideal can be generated by something of this form, and this is generally called a lexicographic Gröbner basis. So you can just do this by a Gröbner basis computation. This is called the shape lemma if you look it up in Eisenbud. And this is one way to solve it, and this is not what we're going to talk about because we're interested in examples where I can't even compute a Gröbner basis in the first place. So you can ask Singular, Macaulay 2, Oscar, to start a Gröbner basis computation, it will not end. I have a lot of examples like that, unfortunately. There's also something called eigenvalue solvers, which is basically derives from the fact that if you have a zero-dimensional ideal, then the polynomial ring modulo to the ideal is a finite dimensional vector space. So multiplication by x1, for example, becomes a linear map. Compute eigen, whatever. Let's not beef too much about it. The way to solve it that I care about, what I want to talk about today, mainly because this is, again, like the source of our motivation. We're not working too much with this technique itself, is the following, and that's called homotopy continuation. So basically, this works as follows. You start with a system that's like, let's pretend it's really, really difficult to solve. Now, how do you solve it? You construct a system that's easy to solve, and then you basically do a path from the easy system to the difficult system. And we all know that along the path, the solutions will vary continuously, right? So there's a continuous path here. So this is like a path in the space of polynomial systems. And then basically you just have to trace one solution to the other. And if your starting system has too many solutions, you will have things going off to infinity. Now, going to off infinity, this is something people in numerics call really, really bad. And this is supposed to be avoided. And one way to avoid this is basically using monodromy solvers. So works as follows. So what I presented at the first was the cookie cutter homotopy continuation. Monodromy solver says you compute one of them, and then you just walk loops around the target system until you get all of them. But again, the problem here is the following. So either you do the first approach I said, and then the question is, how do you avoid these paths to infinity? Or you do the second approach, but then you have to decide, when do you stop? When have you actually reached all the solutions, right? Because you don't know it either. And this is basically the main problem that I want to talk about. So this is the original problem I want to focus on. So if I have a system of polynomial equations, how do we actually construct like optimal homotopies for them? And in this talk, and only in this talk, optimal means basically I have the optimal number of starting solutions and this path that I'm tracking. I don't want to like do basically too much work, essentially. There is a whole slew of numerical problems that can arise if your paths are stupid. I will just, in German we say we put it under the carpet. I don't know what the English word proverb is, but yeah. Now this is a really, really difficult problem, and this is a problem that is basically like impossible to solve like quickly. Of course, I can compute a Gröbner basis, and if I can compute a Gröbner basis, I can get all the information I want. But I want to do this faster than computing a Gröbner basis. So as in classical mathematical fashion, if you're faced with like an impossible problem, you just try to solve something that's like very related to this. And for us, this is in this talk, it's the following problem. Basically, I'm now relaxing my system, and now this is a parametrized system. So the blue kappas are now parameters. And I ask myself, well, for which parameterized systems can I construct generically optimal homotopies? So you know from a classical fact from algebraic geometry, if for generic choice of kappas, the number of solutions is constant, I'm trying to find that number, basically, in a way. And this is what I'm going to talk about. Now, this is something that already, there are some solutions for that. So basically, one possibility, so the question is for which parameterized system, right? So, and one possible parameterized system I can solve this is basically just Bézout's theorem. And that just says if you have a polynomial that's of the form c times x to the power alpha, you have all monomials below a certain degree, and every coefficient is its own parameter, then, I mean, this has that many solutions. I usually denote it by a script L because it's like the length of a certain module. And you can, you know how many solutions it has. And I mean, this is an easy solution you can use to start with because you don't need to solve it. You already know the solutions here, right? So this is one thing you can do. More generally, there is this notion called, there's this BKK theorem, Bernstein-Kushnirenko theorem, that is very similar to Bézout. So now I don't look at all monomials below a certain degree. I fix like finite subsets as I. And I'm basically looking at polynomials with this fixed polynomial support. And then basically the generic number of solution is something we call a mixed volume of the Newton polytope. So the delta of Fi is the convex hull of these Si. And then so the mixed volume is basically how many solutions it has. And you can both construct mixed volumes and starting systems from like mixed subdivisions. So if you don't know what the mixed volume is, here's how it can be computed, for example. So look at F1, that's basically the monomials are 1, x squared, y squared, x squared, y squared. So if you take the convex hull, you get a square. F2 is 1, x squared, y, xy squared. So you get a triangle like this. And basically what you can do is you can take the Minkowski sum of both shapes. You'll get like a bigger shape here on the right. And basically the cells that have both red and blue edges, these are the mixed cells, and the volume is the normalized, or the normalized volume is the normalized mixed volume. So this is what it is and how it can be computed. Just keep that picture in mind. It'll come up later. And yeah, so this is basically what we're trying to do. And we are going to use tropical geometry from it. So I'll just go over this very briefly. You probably all know what tropical variety is. I guess this main slide here is I'm using all pictures in my talks are max pictures. So if you're a min picture person, I'm sorry, you can do a handstand and then that works. So we're trying to solve this problem using tropical geometry. So we're trying to find like generic number of solutions of parameterized system. Sorry, what?
You're restricting to
No. Yes. So we're doing tropicalization on torus. But of course, computing the tropical variety itself is a very difficult task. But there are varieties where it's easy to compute. And that's, if I have a binomial ideal, this is literally just an affine space. If I have a principal ideal, it's dual to some Newton subdivision. And I guess the main reason why we're here is if we have a linear ideal, it's dual to a matroid subdivision. So if you have like linear equations, you can cook up basically like a matroid and a subdivision which is dual to the linear space. And so these are, if you have never seen like these things before, just keep in mind these are like the three cases that are like super easy to compute tropical varieties of. And this is really important for me because these are basically our like almost like Lego bricks for building up more complex tropical varieties. Because one other last ingredient I need is this notion of a stable intersection. So in tropical geometry, you can stably intersect two polyhedral complexes, and it works as follows. So in order to stably intersect red and blue, what I do is I perturb red. So then I have only finitely many intersection points. And then I undo the perturbation, and the stable intersection is just the 3 white points. So the stable intersection is nice because it's either empty or it's balanced of the codimension of the sum. So this is why it's like, I mean, if you have to like define like an intersection product, this is how you do it, because the dimensions add up. And the important theorem here is the transverse intersection theorem. So basically that says if you have two ideals that, if you have two tropical varieties that intersect transversely, then the tropicalization of the sum is the stable intersection of the individual tropical varieties. So basically, and which means, for example, let's just go to the next slide. So if I look at these two equations, computing the tropicalization of the ideal they generate is super easy because I know that they intersect transversely, these individual hypersurfaces. So I know that the tropicalization of this ideal are the points of stable intersection. So in this case, I get 3, 0, and 0, 3, all of multiplicity 4. There's a way to transfer multiplicities as well. This is like, yeah, there's a technical formula, which I will not explain, I guess. In this case, it's basically just the determinant of the arrow, of the directions of the curves how they intersect. So in this case, basically, it's a determinant of 1, 0, 1 minus 2, and then basically times 2 because this has this blue curve came with multiplicity 2 in the first place. Okay. So this is all the basics covered. Let's discuss, and now can take a little bit more time, discuss how the general idea works for basically solving it. And the idea is actually like quite, it's a quite classical idea. And that's basically I'm regarding polynomial system over the Pursue series as one parameter families of polynomial system over the complex numbers. And then the solution over the Pursue series basically describe how the branches look around t equal to 0. And in particular, basically, the valuations of the solutions describe how they diverge and converge or diverge, and in which, if you want, in which like strata at infinity they kind of shoot off to, essentially. And this is classically like known as like the theorem of Pursue, basically. This is why these things are called Pursue series, if you're interested, if you're curious. And if I have, let's say, a parametrized family, if I have a polynomial system over the complex Pursue series, and I have basically two like different clusters of roots that diverge like in different behavior, what I will end up capable of doing is basically have like targeted chains of coordinates that basically make like subsets of these roots actually converge. And this is what I'll be using to for solving the solution. So basically, if I can get a picture like like here on the middle column, what I can do is I can basically compute all 4 solutions on the right-hand side by taking these 2 solutions, tracing them to here, and taking the blue solutions on the left and tracing them to the right. Yeah. So let's check how this is done on a concrete example. So suppose now you have this polynomial system that you already saw before, very similar to something you saw beforehand. And suppose I want to solve this for this choice of parameters. So I set like parameters to be 3, 1, 4, 1, and 2, 7, 1, just randomly chosen. And let's just pretend it's super hard. Okay, you don't know how to do this. Then using these tropical homotopies, what you would do is you basically pick like a generic specialization. So basically you add like random powers of t to your parameters. In this case, I just picked t to the power 6 here and t to the power 6 there. And then you trust in some kind of tropical black box. And what you need to then you pass through some black box, and you basically all you need is this data of your tropicalization. So you need to know what the tropical points are, and you need to know basically what the solution sets of the initial ideals are. This is like, if you're familiar with that, good. And if you don't, then just ignore these 3 parts. And in my case, basically, I could get this very cheaply just by looking at the intersections. So I didn't have to do any like complicated computation for this part. And now what I can do is the following, just algebraic manipulation, if you want to say. So for example, for 0.30, I'm basically looking at, okay, let's just go slowly. I look at f1 basically, and I shift x by t to the power -3 and y by t to the power -0, which because of the 0.30. And then I just multiply like by a power of t, everything. And then basically I get an expression like this. And you can see that basically for t is equal to 1, this is basically the system that I want to have. And for t is equal to 0, this is binomial. And similarly for the other one. And this is not a coincidence. So if you do this right, basically, and you can do this for the other one as well, for 0, 3, you basically then now shift x to t to the power -0, y to t to the power -3. You just multiply by a sufficiently high power with t, so you only have positive exponents. And again, for t is equal to 1, it's exactly what you have on the front. And for t is equal to 0, both are binomial. And this is so this is basically how you get these homotopies. And this, what I've shown you here, is basically known as these polyhedral homotopies. So this is like invented, I think, by Huber and Sturmfeld like almost 30 years ago, basically. And this is the go-to method. So if you let's say you are interested in solving polynomial systems and you open up, let's say, homotopic continuation JL, and you ask, give me the solutions. This is what it's doing in the background, basically. This is polyhedral homotopies, but okay, the general math behind the idea basically works in general as long as this data is, I can compute it very, very cheap, right? So and basically the challenge really is, how do I get this data really, really cheap? Now, what I've shown you was perfectly what worked out very nicely because all the tropical hypersurfaces intersected each other transversely. But there are a lot of examples. So, I mean, you just have to trust me with this. There are a couple of examples where, regardless how you choose the parameters, they will never intersect transversely. And this is actually also the more interesting case, because if I have transversely intersecting like hypersurfaces, the number of solutions will always be the mixed volume. This is like something you can prove. So this is actually the interesting part, more like, and that happens quite a lot in applications. So you have very few solutions. So it happens quite often that like you look at the system in the applications and it has frustratingly few solutions than you believe. I think just that I think just that the equations that arise in applications, they are not random enough. There's some structure in the coefficient, there's some structure in how the parameters are distributed, and because of that, you never have mixed volume many solutions. Which is really, really good because the mixed volume can be really, really, really large. And another question. Okay, yeah, and I had like funny interactions where basically I did a big calculation and I got I was very surprised. I got two solutions. And then the biologist was like, of course there's two solutions. This is like regulating like some kind of whatever mechanism in you. I forgot, honestly speaking. It was like regulating some kind of mechanism in your body. Why would you expect more solutions? And I just see like of this like giant list of polynomials of high degree. I was like, why would you expect there are two solutions? As like, okay, sorry, this is a little bit off topic. So what to do you cannot? So if you ask Hannah, what do you do if you have two tropical curves that intersect each other non-transversely? Then the answer is clear. You modify, right? So you basically, so there's this paper by Goethe and Markvik. It's like repairing tropicalizations with modifications. And I'll show you how it's done. You basically introduce a new variable and you basically try to separate these two things in a third dimension, basically. That's what we're going to have. So think of these two as like, separate them in a third dimension. Let's put this. And here's how it's done. And again, I have to show this on like some concrete example. So consider, for example, this type of parameterized system that's commonly referred to as a vertically parameterized system. And this is a system where basically every monomial x to the power alpha j has its own parameter aj, basically. But these parameters aj can basically appear in multiple fi's. So a very simple example thereof is basically this chemical reaction network that I showed in the beginning, right? So take a look at, for example, kappa 3. Kappa 3 only appears in front of x to the power a, x to the power, sorry, xa, xb to the power 5. And kappa 4 only appears in front of the monomial xa cubed xb. So every parameter, okay, sorry, the parameters here are called a, they're kappa in the bottom, but every parameter is tied to its own monomial, and that's exactly where it has to stay. Now, how would you basically, and if you basically write down now the three tropical hypersurfaces, you'll see that they are actually overlapping quite a bit. And that's because they share a lot of same monomials. The monomials, if you insert some random Pursue series, they have the same valuations. This is bad. But what you can do is you can basically introduce a new variable for every previous monomial, and then your system now looks like this. So you had your three original polynomials, but now instead of a monomial in x, you just have a simple linear y. And now I'm also beginning to home in why I'm actually in this conference here in the first place. But now I have these, so y1 is basically xa, xb, xc, y2 is xa, xb squared, xc, and so forth and so forth. And now what you can show, if you have this type of, these two equations, what you can show is that if you now choose like a generic choice of parameters, so again I have m parameters, then the original tropicalization is a stable intersection of these two constituents. And what's really, really important here is that each of these constituents was very, very easy to compute. This was linear, this is dual to a matroid subdivision, and these were hypersurfaces, they're dual to Newton subdivisions. So this is basically a type of system where for generic choice of parameter, it's super easy to compute the tropicalization. There is some added technical, details here. So basically, if you remember, in order to compute the solutions, I needed like the initial ideals and solutions thereof. And you can even you can show that you can compute the initial ideals as well. So if, for a point on the tropical variety, you can compute the initial ideal by computing a Gröbner basis of the linear part. That's super easy. That's Gaussian elimination. And then all you have to do is back substitute the x. And you will see that this is still binomial. So it's super easy to solve as well. So binomial ideals, by the way, are easy to solve. So we like them. So this is basically one example of a class of parameterized polynomial systems where I can easily basically get everything I need to solve them optimally using tropical geometry. Yeah. Yes, yes. So initial ideals commute with like this map, basically. Initial ideals here are mapped to initial ideals here, more or less. Or I guess under this toric re-embedding, like this is just re-embedding my original ideal. Another example where this works is the following. So this is a different type of example that also arises sometimes in practice. And that is basically, I now fix, instead of monomials, I'm fixing like polynomials, S1 up to Sm in my polynomial ring, or Laurent polynomial ring. And then basically I have parameters aij in front of every polynomial now. And the fact that this is now a polynomial and not a monomial will make things much more difficult, will make our life much more difficult. So here's an example thereof. So here I have my polynomial support would be x1 squared plus x2 squared, that's s1. S2 is x1, S3 is x2, S4 is 1. This is a polynomial support, and now I'm in a case where the parameters, so this is usually called a horizontal system. And this is now every parameter is bound to the equation. So A1 up to A4 only appear in F1, A5 up to A8 only appear in F2. And I can do like a very similar picture. So I can do basically a very similar procedure, and I basically introduce new variables for the y's and split them as follows. So I basically introduce y1 for this, y2, y3, and y4. And you can similarly prove then that the tropicalization for IQ is basically for generic choices of parameters that basically decomposes into a stable intersection of hypersurfaces. And again, it's super easy to compute. I can compute all the initial ideals that I want, and everything works out nicely. So these are like two types of polynomial systems that can again, like the whole reason why we want to do this is I want to solve like the equations that I have in front of it. And this is basically the entire tropical machinery that boils down to that. Okay. So there is one problem though. It's not like everything is super easy. And here I'm basically looking at an example that can be found in one of the papers by Heather Harrington and Bernd. And this is like okay, I'm not really writing down the entire system. So the system has like 19 variables, 22 quadratic monomials, and yeah, there are like 19 equations as well. So it is a square system. And if you do this procedure that I said, you will basically get 19, again, you still have the 19 variables in X. Every monomial now becomes a new variable Y. So you basically have like different, and you have basically 14 plus 5 linear equations and 22 binomial equations for the different Ys. And so let's do the same thing that I said we will do. Let's compute the intersection. And I hope that in this audience, nobody will look surprised if I tell you that tropical linear spaces are really, really difficult. So if you compute the tropical linear space for the linear part, you get like 250,000 cells, which is not that bad. You ask Polymeg, you ask Oscar, you'll get that really, really fast. It's not that problematic. What is deeply intellectually unsatisfying is the fact that if you now intersect with this, oh, okay, by the way, binomial is just one cell, right? It's just a linear space we talked about. So if you now do the intersection, these 250,000 intersections, you get 9 points. Only of the 250,000 things that you computed, you needed 9. If you do the calculation in your head, you literally throw away 99.99 whatever of your calculation. I think I did it once, it's like 996. So this is like, it is fast, you can do it, but it just doesn't feel like a really, really clever algorithm if you basically end up computing stuff and you throw away like 99% of what you have computed. So there must be a better way to do this, right? So how do we get this? So how do we do this computation? So how do we compute this intersection without computing the intersects in the first place? This is the first type of but this basically summarizes the first type of tropical homotopies. So this is using tropical geometry to solve these polynomial systems. And now I'll tell you about the different types of tropical homotopies, and that's how to compute this intersection without computing the intersect. Yeah. The intersects, the stuff that I'm intersecting. Yes, exactly. Yes, I promise it works. It makes sense. And this is how it's done. So suppose I have hypersurfaces, linear spaces, whatever, something that's tropically dual to like some polytope or polyhedron or subdivision. And I want to compute the intersection. So in this case, I have two tropical curves intersecting 1 point. In the other example, yeah, so I had like 9 points at the end. Now what I do is basically I start with hypersurfaces that are basically set theoretic linear. So these are technically, okay, sorry, I didn't really write the multiplicities. There should be multiplicity 2 on every edge. So these are tropical quadratic hypersurfaces. But set theoretically, if I forget the multiplicity, it's linear. It looks linear. And this is why computing this one white intersection point is super easy to compute, because it's just linear. But I just have to keep in mind this white point is actually something of multiplicity 4. So basically, start looking at these target hypersurfaces that I don't know how to intersect. I basically construct these set theoretic linear hypersurfaces. I mean, if one of these, if red were a tropical linear space, I didn't have to do anything. I just use a linear space, basically. And now I do the following. I basically look at the coefficients of the polynomial here, and I basically change them from here to what I want to have at the end. So yeah, so basically, if you take a look, let's say at the blue triangle here, so what needs to happen is that, okay, let me just draw some quickly. So the blue, let me just check that. So this is what I want to end up with, and this is how the blue looks at the beginning. So what I need to do is I need to take this point and I basically move its height to infinity. That's how you can think about it. So basically, this is a polynomial. This is a Newton subdivision, and moving this to infinity. Oh, by the way, this is I'm taking these pictures. I've taken from Anders Jensen's paper on tropical homotopies. So he's the person who basically came up with this. And so if you now move basically the topmost edge, so these are all regular subdivisions. So if I move this height basically now to infinity, what happens is first, if you move it a little bit, you'll break off the blue curve basically breaks off a little bit. So you get if you increase the height, you will induce like a fold in the subdivision, and the dual tropical curve now looks like this. And if you basically move this point to height infinity, then this vertex basically shoots off to infinity, and you're just left with the clean tropical curve like this. Now you can do the same thing. Now you can basically adjust the height a little bit so that you get a different subdivision. So the subdivision that you see on the right-hand side is just the subdivision of the Minkowski sum that you get from the product of these two tropical polynomials. So you basically shift the heights a little bit, and then the intersection point goes from here to here. And now you can do the same thing with the red curve. So in the red curve, basically, I only need this bottom part. So there are multiple points I need to break off. So for example, what I'm doing first is I'm taking this point here, and I basically take its height and move the height to infinity. If I increase the height, I will induce a subdivision, an edge in a subdivision like this, and the tropical curve looks like this on the right-hand side. And if I basically move this height to infinity, then this becomes like that. And then in the final step, what I need to do is basically, if I now adjust the valuations so that this red subdivision moves to the left-hand side here. So basically what I do here, okay, it's probably easier to see on the curve. So now I can move the red curve basically to the right. I get 2 points in this computation. And now all I need to do is basically move this point, the height of this point of the red subdivision to infinity. So if I increase it a little bit, the red curve breaks again. And if I basically move then, if I let this go to infinity, I will get to this, this picture that I wanted. So this is how tropical homotopy works by Anders Jensen. And now okay, this kind of looks very complicated. I mean, like not mathematically complicated, but just still look quite involved. But what makes this really, really fast on a computer, and this is really like one of the strong points in tropical geometry, is that you didn't really have to do this picture, like you didn't have to do this computation like with a global picture like I visualized it. It actually sufficed. So if you do this in a computer, the computer will not track the blue curve and the red curve. The computer will just only track how these curves look like around this intersection point, right? So basically, in the first 3 steps, nothing has changed for the computer. The computer will basically just take this height, let it go to infinity, and just realize nothing here changes. There's nothing to do. And only basically in the 2 vertical steps and this final horizontal step, something changes with the intersection point, and there you have to do some non-trivial computation. This is not the case in classical algebraic geometry. So if I give you like, if I take a tropical curve and I zoom in to like a small point, you have no idea how the original tropical curve looks like, right? So I could take like, I can take like a very complicated tropical curve. Okay, pretend it's very complicated. I zoom in on one point. It looks like this. you can't really reconstruct a tropical curve. In classical algebraic geometry, you still could, right? You localize at the point and at the prime ideal, you can basically still like somehow cook up, well, okay, you can cook up like the irreducible component where you kind of started out with. So you don't really, in algebraic geometry, you don't really lose a lot of information. In tropical geometry, zooming in on the point loses a lot of information, but this really works out greatly because this makes our life here so much easier. And also, this is the whole reason, like if you like, let's say, degenerate something torically, why what you end up with is so much easier to deal with than what you had beforehand. Yeah. Oh, no, sorry. No. Oh, every move that you see here in front of it is basically adjusting the heights of the tropical polynomial. So these tropical curves are dual to like subdivisions on the Newton side. Okay, so let's just, so basically if I have let's say one, yeah, so let's just take a tropical polynomial 1x squared plus y squared. Then basically this is how the Newton polytope looks like. The tropical curve, this is also why I like Mach's convention. It's literally dual to this. And this point here is the W. So if this is F, this is the point W such that F of W is attained thrice. So this is like a max of 1, 2x, 2y. So in this case, I guess, yeah, this would be minus 1/2 minus 1. Plus 1/2 plus 1/2. So basically, this is, and if I would basically now, for example, add an x to this, like with a high negative number, for example, then the subdivision that I would get, I would basically induce like a cut here, and the tropical curve would look like this. So every move I'm doing is basically adjusting the coefficients of my tropical polynomial and changing the dual picture. Ah, sorry, this was probably not really readable from the other side. But yeah. Yeah.
If you are adjusting, you are trying to track the solution, right?
Yes.
At some point you said we send something to infinity. What do you do with the solution that disappears?
There is no solution. The only solution, the solution I'm tracking is the white point. So the blue curve. So yes, if I take this, if I let, yeah, okay, let me just do it here again. So if I take, let's say, this Newton polytope, and let's say I'm looking at f x is again equal 1, sorry, plus x squared plus, let's say, c times y squared. Okay, and let's just add a y for good measure. And now I let basically c go to infinity. Then what happens is basically at, sorry, I'm using max, so I should be going to minus infinity. Then basically the polynomial changes, the subdivision changes, but the solution, the white point, doesn't change because it lies on, it lied on like this part of the blue curve, basically. So yeah. So basically, I'm intersecting like a lot of like these tropical objects, and these tropical objects arise, let's say, from polynomials, but not every monomial has to like contributes to every maximal cell on the tropicalization. And this is what's kind of happening here in this point, basically. So if I increase now the valuation, the blue curve kind of breaks, but if I only care about the white point, nothing changed, actually. And the computer won't even register it. It just does this like implicitly, which is what makes it fast. Okay. Yeah, so this is how homotopies work in the solution. And this, I mean, I've shown you like the example with two hypersurfaces, but the same is actually also true if one of them happens to be a linear space and it's dual to a matroid subdivision. The only reason why I didn't do this is because it's much more difficult to draw, right? So basically, in this case, I'm intersecting a blue tropical line that's dual to the bipyramid that you see on the, okay, that you get if you contract the red edges. I intersect it with the red hyperplane, a hypersurface that's dual to basically this edge here. And as I move basically the red hypersurface up, the subdivision and the one intersection point becomes 2. The subdivision also changes. So basically, this is something I can do as soon as whenever I know that the tropical variety is dual to like some kind of dual object, basically. Let's put it like this. Okay, so this is the second type of tropical homotopies, and they basically the bottom line, essentially, of this talk. There's another slide with open questions, but the bottom line that I usually like to pitch to people who do like numerical algebraic geometry is before I keep telling them that before they solve a system over the complex numbers, maybe they should try to solve it combinatorially over the tropical numbers first, and this will help them in making their numerical computation over the complex number much more stable, basically. This is that part. But now let me just finish with a couple of like open questions, essentially, and that is like what I maybe want to talk about. Sorry. Okay, so I talked a little bit at the start about repairing tropicalizations with modifications, and one question that basically I've been thinking about a lot, but also I think a lot of people here have been thinking about, maybe not from the same background, but that's basically which parameterized systems have like a recipe for tropical modifications. So I know like, so for example, if you have like given polynomials that have some parameters. So for example, these polynomials could be could describe, let's say, the bitangents of a plane quartic curve. So you have different plane quartic curves. So you have a lot of parameters there. And what Goethe and Markvik showed is basically whatever your parameters you choose, there's a way to modify it to get a nice, clean tropical pictures. And this is exactly the type of question I'm interested in, right? So what type of parameterized systems are there that I can like actually give like a recipe for modification to repair it? This is very useful for like a lot of like any of these recipes would be super useful for practical reasons. Let me just reiterate because of so what's important for this recipe is that, well, first of all, I would ideally like this parameterized system. If I think of this as a family of polynomial equations, I want this to be like large. So for example, what I'm less interested in is like a parameterized system where the number of parameters is 0. Then yes, you can repair that, but it only applies to the system that you have at hand. Ideally, this should be like a large family. And what I also want to end up with, this I should be this Mathcal I, is I want to have intersects that are easy to compute or desire. So for example, in Goethe-Markvik, these are hypersurfaces. Wonderful. Now, what is not so important, and I think I also need to stress this because of where my motivation originally comes from. So it's less important to me that actually this F arises in some application. Like I talked about, this robot arm and these chemical reaction networks, but this is really not important for this type of question. Because even if, like your family does not arise in like some kind of practical application, that it's useful as like, if I have a concrete like system that I want to solve, I can usually relax it to like your family, for example. So in the I was actually also lying a little bit. The chemical reaction network examples are not these nice vertical systems that I've pretended they are. They are a little bit more nasty, but they can reduce to these vertical systems. So if you have like a parameterized family, where you have a nice recipe for modification, but this doesn't happen to come from like some kind of robot engineering, I don't really care, right? These are tools in the toolbox for me. And I also don't really care, some people do, like there are lots of works to do this, but I don't really care that the final number of intersection points is less than the original mixed volume. There's a lot of work in the applied algebra community in proving that something has fewer solutions than the mixed volume. I don't really care about that. I just care about how many solutions it has, and if that happens to be equal to the mixed volume, well, then knowing that is still better than not knowing at all. So that's like the first type of question. It's all these modifications. The second type that might be more interesting for people with a background in matroid theory is the following. So I talked about this like tropical homotopy. So so basically that's like I have a tropical linear space and I want to deform it to a different tropical linear space. Let's think about it like that. And the question really is that what is like a canonical path in the Grassmannian that I can take to move from one tropical linear space to another tropical linear space? Now, and one class that's super useful for these type of paths is these tropical linear spaces called Stiefel tropical linear space. So basically, these are all tropical linear spaces that can be written as a stable intersection of hyperplanes. This is like Fink and Rincon, maybe, I think. Now, these are really, really nice to deal with. And OK, one thing that there are a lot of reasons why they are nice theoretically. Let me just tell you why they are really, really nice for my application. And that's because dealing with the general matroid polytope is horrible, right? They have a lot of vertices and a lot of bases. And if you have to actually work with it on a computer, it happened multiple times that my computer crashed because I couldn't allocate enough RAM to just fit the matroid polytope into my memory. So, but for these tropical linear spaces, I don't have to keep track of the matroid of this of the matroid polytope of this tropical linear space. All I have to keep track of is k individual matroid polytopes. So in a way, so if you have heard of like lectures in numerical algebraic geometry, this is almost like some kind of low-rank approximation of a matrix, basically. This is a way to compress the matroid polytope. Now, this is tropical linear spaces. The Stiefel tropical linear spaces are super nice, but the problem is there are very few of them compared to all possible tropical linear spaces. There are very few like transversal matroids compared to the set of all matroids. So, but what about, like tropical linear spaces that are almost like them? So basically, these are tropical linear spaces that are not the intersection of k hyperplanes, but maybe k minus 1 hyperplane, k minus 2 hyperplanes, and then basically one tropical linear space of codimension 2, right? What about this? Or, I mean, you can go further. What about tropical linear spaces that are basically a hyperplane intersected with something of one rank higher, basically? So there are many more of them, and honestly, any partition of k will give you like one decomposition. And what is really nice for me is basically that keeping track of these two matroid polytopes is so much easier than keeping track of the matroid polytope of this big thing. And it's so much easier to work with. So this is like why I kind of care about this. And I guess the natural question for me is, if you have a tropical linear space, what is actually like the nearest, like almost Stiefel tropical linear space? I don't really know how to call these things, by the way. But yeah, so if I have like a fixed, if I have like pick a tropical linear space that I like, the odds of them lying in one of these strata is like very, very low. But maybe there's something that's close, and I can approximate it by something that lies in them, and basically work with that numerically at least. That is like the type of question I'm interested in. If you have any like idea of like literature that have dealt with these type of problems, please let me know. I'll be very nice. Yeah, would be very interesting to hear you. And then otherwise, yeah, thanks for listening.